Hello guys, my name is IBM and today I'm taking you to uh, lesson 3 of Electricity and DC Circuits. I think basically in lesson 3 we shall explore concepts of electrical resistance and resistivity. So lesson 3 will basically concentrate on electrical resistance and resistivity, where we shall explore resistance as a concept. We shall talk about measurement of resistance using an ohm meter or a multimeter on the ohm setting. We shall talk about Ohm's law, not forgetting the IV characteristics, the characteristic graphs of several components which are necessary for this curriculum. We shall talk about the relationship between resistance and resistivity. And I think we shall do a few examples about resistance and resistivity as a very important concept for this lesson. We shall also or we shall also obtain or derive several relationships between resistance and other quantities. We shall explore the factors on which resistance depends in lesson 4. Do not forget the course outline for AS Physics 9702, where you study physical quantities and units, errors, uncertainties, treatment of uncertainties, kinematics, dynamics, force, density and pressure, work energy and power, deformation of solids, waves and superposition, electricity and DC circuits, and currently we are concentrating on electricity and DC circuits. So this is going to be lesson 4, and most of the concepts we are going to discuss here relate to what you already studied in GCSE, only that we shall just slightly advance, or we shall just slightly add more flesh on what you covered in GCSE. Okay, let's start with electrical resistance and resistivity. In lesson 2, we distinguished EMF from potential difference, where we saw that the EMF was the energy transformed by the power supply to to a charge, and we saw that the PD was the energy transferred by the charge to the component in the circuit. So we saw the relationship between PD and EMF. If we said that if the battery is not supplying a current, then the PD across the battery is the EMF. But if the battery is supplying current, then the PD across the battery is actually terminal PD, as we shall see later on. So we notice that if a lamp is connected to a battery, a current in the lamp causes it to glow. That one we are much aware of that. But what determines the size of the glow or the brightness of the glow is actually what we are going to explore in this lesson. We know it will glow, but what will make it glow brighter or dimmer? So the current which is going to cause or the current which is going to flow to cause a glow of the lamp is going to depend on two factors. The first one is the potential difference or the voltage across the lamp. And of course, we know that if the potential difference is greater, then through the current through the lamp is greater. That is in accordance to Ohm's law, which we are going to see today. Then the second one is going to be the resistance R of the lamp. If we want the lamp to glow brighter, then the greater the resistance, the smaller the current for a given potential difference across the lamp. So it's like the current which flows through the lamp to cause it to glow depends on two factors. Number one, its resistance, and number two, the PD across the lamp. So these two factors, PD and resistance, are going to be very important, and they are the ones we are going to explore in lesson 3. We notice from IGCSE that a good conductor has a low resistance, while a good insulator is actually a bad conductor. It has a high resistance. So insulators have infinitely high resistance, so they don't easily conduct. So if the resistance is high, we notice that the current flowing through the conductor is going to be low. And if the resistance is low, the current which flows through the conductor is going to be high. So generally, metals such as silver and copper have very low resistances, and they are used in connecting wires and cables in electric circuits. Most of the wires at home, or most of the wires in the electronic devices or in the electrical devices, connecting wires in the chargers and so on and so forth, most of them are made out of copper, simply because these materials or these metals have low resistance. And the lower the resistance, the higher the current flowing. Of course, the higher the resistance, as we shall see, the higher the resistance of a conductor, the more energy is going to be lost within the conductor to overcome this resistance, as we shall see later on. So, a substance or a device which resists the flow of electric current is called a resistor. A device or a substance which resists the flow of electric current is called a resistor. Now, someone will say, can we say a good insulator is a resistor? In most cases, the devices we are talking about here are going to be conductors, but these are going to be conductors which do not actually easily permit flow of electric current, and they're going to be called resistors. You might have seen resistors in the laboratory. You remember the electrical symbol or the circuit symbol for resistor from lesson 1. And in the laboratory or any other scientific laboratory, you should be seeing such devices. These are what we call resistors. They look like this. You might have seen them in your laboratory. So, a substance or a device which resists the flow of electric current is what we call um, a resistor. To distinguish it from an insulator, even though we say it has an infinitely high resistance, a resistor will permit flow of current, but it will reduce the flow of current through a device. In other words, we are going to see later on that resistors are normally used to protect a circuit, to reduce the current which reaches a certain component in a circuit. That is the purpose of most of these resistors. For example, they may be used to protect diodes because diodes may require less current. So to reduce the amount of current reaching the diode, we may add a resistor which has high resistance. Yet, if we were to put an insulator, then there would be completely no current flowing, and therefore the diode wouldn't work. So any substance or device which resists or reduces the flow of current or electric current in a circuit is what we are going to call a resistor. What is the relationship between resistance and potential difference? Because we saw that the current flowing through a device depends on two factors, the potential difference across the device and the resistance. So what is the relationship between those two? So electrical resistance is going to be defined as the potential difference per unit current through a conductor. That is, we shall define resistance as PD divided by current. Now, the definition of a resistor that I gave as a device which resists or reduces the flow of current in a device cannot substitute for defining a resistance in physics. You cannot define resistance in physics using an English meaning of the word resistance. So I can't define resistance as the opposition to flow of current in physics. Rather, because current through a device depends on PD and the current, then I can define resistance as the potential difference per unit current through a conductor. That is, resistance is equal to PD divided by current. That is the definition of resistance. Potential difference divided by current. Potential difference per unit current. That is going to be the resistance. In other words, using symbols, resistance is going to be equal to V over I, or you can make any of the quantities the subject. So I is V over R, or V is equal to IR. Resistance is measured in ohms. You mentioned this in GCSE, and the symbol is read as omega, but it represents ohms. So resistance is measured in ohms, in memory of a certain scientist called Ohm. I think this is the only unit named after a person, and the first letter is not representing the symbol. The first letter of the name is not representing the symbol, but then it is a different letter which is representing the symbol ohm. So because the resistance is PD per unit current, then from the definition of resistance we can define the unit for resistance. It is PD measured in volts divided by current measured in amperes. So we can define an ohm as a volt per ampere. So the ohm is going to be defined as 1 volt per ampere. I mentioned earlier on that we can define quantities in terms of other quantities, and we define units in terms of other units. So we are defining the ohm as 1 volt per ampere. That is the definition of the ohm, 1 volt per ampere, because the ohm is the unit for resistance, and the resistance is PD divided by current. Okay, so before we advance, let's do a very short, simple self-check, remind ourselves about concepts of IGCSE. Question 1. What PD is needed to make a current of 2 amperes flow through a 30 ohm resistor? So PD is, we have already said that resistance is equal to V over I. So V is equal to I times R. So you just substitute and you get 60 volts. Without calculation, what PD is required when the resistance is doubled? So resistance is directly proportional to V. From the formula, resistance is directly proportional to V. So if the resistance is doubled, the PD is going to be doubled. So the PD is going to be 120 volts without calculation. The PD is also doubled because the resistance is directly proportional to the PD. A PD of 240 volts across a resistor causes a current of 80 milliamperes to flow through it. What is the resistance of the resistor? So resistance is equal to V over I. So V is 240 divided by I, which is 80, but is in milli. So we say 80 times 10 to the power of minus 3 to remove the milli part. So I'll just check with my calculator. 240 divided by 80 exponent minus 3. So the resistance here is going to be simply 3000 ohms. What PD would cause a current of 40 milliamperes to flow through the resistor? So the current has been changed to 40 milliamperes. Of course, the resistance of the same resistor is a constant. So we want to find the PD. What PD? So V is equal to I times R. So this is going to be 40 times 10 to the power of minus 3 to change it to amperes, then times the resistance, which is going to be 3000. So 3000 times 40 exponent minus 3. So this gives us 120 volts. Without calculation, you could also arrive at that answer because you notice that V is equal to I times R, which means V is directly proportional to R. Initially, the current was 80 and the PD was 240. 40 milliamperes is half of 80. So the resistance has, the current has been, PD is directly proportional to I. If the current has been halved, we expect the PD to also be halved. So it was initially 240, so it makes sense for us to have 120 volts. What current flows when a PD of 7.5 volts is connected across a 2 kilo ohm resistor? So we want current, making current the subject. Current is going to be V over R. So V is 7.5 divided by R, which is 2 kilo ohms. So that is 2 times 1000 to change it to just ohms. So I'll just press my calculator. 7.5 divided by 2 times 1000. So the current is going to be 3.75 times 10 to the power of minus 3 amperes. Okay, that is just to remind us of IGCSE concepts. Let's continue with electrical resistance and resistivity. So how do we measure the resistance and how do we represent a resistor? Let's talk about the rheostat first. So the rheostat is actually like a resistor, but this time this resistor, its resistance can be varied. It is actually like a wire whose resistance can be varied by just a sliding contact. So the amount of current that flows through a resistor or a resistance wire can be reduced if the length of the wire is increased. Later on, we are going to see that resistance is actually, later on we are going to see that resistance is actually directly proportional to the length. So the amount of current that flows through a resistance wire can be reduced if the length of the wire is increased. So this can be reduced by a variable resistor, or a variable resistor which is called a rheostat. So we can use a device whose resistance can be adjusted by simply changing the length of the wire which is making up the resistor. So we form what we call a variable resistor, a resistor whose resistance can be adjusted to a required value. This is commonly called a rheostat. So a rheostat consists of a coil of constant wire wound on an insulated iron former. The length of the resistance wire through which the current passes is determined by the position of the slider, which provides an alternative path of very low resistance. So you remember the symbol for a resistor was basically something like this. That was a fixed resistor. But then, if we want a resistor whose resistance can be varied, that is going to be called a rheostat or a variable resistor. This is how a rheostat looks like. In your laboratory, you should be having something like this. And of course, these wires show the correct connections of the rheostat. If you are connecting a rheostat to any circuit and you want to be able to vary the resistance, because when I connect it here, this is joined to this contact here. And of course, this is joined to the wire. So as I slide this, I reduce the distance or the length of the wire in play. I will reduce the length of the wire in play if I slide this to the left-hand side. So rheostat looks like that, and this is the correct connection of a rheostat. Now, of course, I always see my students in a class when they are connecting a rheostat in a circuit, they end up connecting, they put terminals here and here, they connect the circuits here. Here you have fixed the rheostat is not now doing its work. It can't change its resistance because this wire which is wound onto the soft former is of the same length if you connect to this point and this point. But if we connect to this point and here, it means that as the sliding contact moves, it means the length of the wire which is constant is being reduced. So that is a rheostat. So in your laboratory, you should be able to see that. The symbol of a variable resistor looks like this. This is how we represent a variable resistor or a rheostat. You can draw this one here. It is still a variable resistor. This is showing a sliding contact. We shall need this in the last part of physics, which is potentiometer. I mean, in the last part of electricity, the last lessons, which will be potentiometers and potential dividers. So I can represent a rheostat like this, or even like this. This can also be a rheostat after it is a variable. It's a variable resistor. But this one is better because this arrow here shows or indicates that the fixed resistor or the resistance wire, its resistance can be varied by just moving the sliding contact. So this is how we draw a rheostat in the symbols in a circuit, or you can even use this one here to represent a rheostat, but this is most likely going to be a variable resistor or a resistance box. So a resistance box has its values of resistance adjusted by plugging out or plugging in some of the terminal or some of the keys to change the resistance. Okay, so I have talked about a rheostat, which is very, very important. You might also have mentioned it in GCSE. How do we measure resistance? So to measure resistance, we use a device which we call the ohm meter. The ohm meter. An ohm meter looks somehow like this. With, of course, you just look at this and know that this is an ohm meter, but it can be a multimeter with it can be a multimeter with its pointer on the ohm setting. So it can be an ohm meter or a multimeter on the ohm setting, because a multimeter it serves a lot of purposes. A multimeter, we saw it can be used to measure current in lesson 2. We saw it could be used to measure voltage in lesson 2. But a multimeter can also be used to measure resistance as long as you set it to ohms. So a multimeter on the ohm setting can also be used to measure resistance. So the ohm meter or the multimeter can give you the resistance, can give you the resistance or directive values of resistance. Resistance can also be measured using an ordinary ammeter and voltmeter, but this time both of them must be used at the same time. So in a circuit, you must put an ammeter and also add a voltmeter because we know that the resistance R should be equal to V over I. So I can't say I will use the ammeter to measure resistance or I will use the voltmeter to measure resistance, but I must use both the ammeter and the voltmeter because the resistance is V over I, where V is the PD measured using a voltmeter and I is the current measured using an ammeter. So in the absence of an ohm meter or a multimeter which you can set on the ohm setting, then you must use both the ammeter and the voltmeter because this will not give you a direct method or direct value for resistance, but it will give you values to use to obtain the resistance. So if we are using the ammeter and the voltmeter, then we must do something like this. The voltmeter must be connected across the resistor, and then of course the ammeter is in series with the circuit. So measuring V and measuring I, we can be able to find the resistance of our resistor here. Yet for the ohm meter, I just put it across the resistor and it gives me the resistance. For the multimeter, I just put it across the resistor and it gives me the resistance. So at the start, the rheostat is adjusted to maximum value. Then a switch is closed and the voltmeter and ammeter readings V and I are noted. The setting of the rheostat are gradually reduced and a series of readings V and I are noted and tabulated. This circuit is going to be used to verify what we call Ohm's law. So instead of getting a single value of R as V over I, in my circuit I have incorporated a variable resistor so that I can adjust the I can change the V and the I so that I'll have a table of values where I have V measured in volts and I measured in amperes, and then I'll be able to plot a graph. So instead of getting a single value, which may have a lot of uncertainties, I would prefer to get several values by adjusting the current flowing through the circuit and the PD across my fixed resistor R. Then I'll then plot a graph, either a graph of I against V or V against I. So this circuit is going to help me to verify what we shall later on call Ohm's law. So what is the relationship between V and I? Depending on the device or the quantity we are considering here, or the component we have connected in our circuit, this circuit is going to help us to tell the relationship between V and I. And of course, that relationship is going to give us what we call the resistance of the component we are considering. So this is the circuit we need to verify what we shall call Ohm's law. So one, I've said we could measure the resistance using an ohm meter directly. We could measure the resistance using a multimeter on the ohm setting directly. However, in the absence of those two, we could measure the resistance using a circuit like this one, where we have a voltmeter connected across the device whose resistance is required, and we have the ammeter in series with the circuit. So to give a more reliable value, instead of just obtaining a single value, we could add another resistor whose resistance is known and can be varied. So this is a variable resistor. The purpose of this variable resistor is to change the current, which is also going to be changing the PD across our fixed component or our fixed resistor. So by obtaining several values of V and several values of I can plot a graph later on, which graph will give me the relationship between V and I. And of course, that relationship will will give me a lot of information about the resistance of this resistor or the resistance of this component. And I said this circuit will therefore be used to verify Ohm's law. You may be asked to draw a circuit diagram to verify Ohm's law. Remember, this is AS, it's no longer IGCSE. So let's talk about Ohm's law. You did not mention Ohm's law in IGCSE, I'm certain about that. So when a graph of V against I for a metallic conductor, from the circuit we have just seen previously, if we plot a graph of V against I for a metallic conductor, we would expect to get a straight line like this one. Why? Because for a metallic conductor, the potential difference across the conductor is directly proportional to the current. So a straight line through the origin is going to be produced if we consider a metallic conductor or a metal wire. If we consider the resistor we have considered in the previous slide, which is just a metal wire, and continue adjusting the variable resistor, we will notice that for the different values of V plotted against I, we will get a straight line through the origin. So this straight line, the straight line shows that I is directly proportional to V. I is directly proportional to V. And the gradient is going to be constant because it's a straight line through the origin. So the gradient is constant. This only happens if the temperature of the conductor does not change. So if we have a metal wire and the temperature of the wire does not change, it means the current is not big enough to cause the wire to heat up, then we would see that the current is going to be directly proportional to the potential difference, which will give us a straight line, only if the temperature of the conductor remains constant. Of course, later on we shall see that if the temperature does not remain constant, then resistance changes because resistance is affected by temperature, as we shall see later on. So this relation is called Ohm's law. This relation, the relationship between I and V being a straight line is at constant temperature, is what we call Ohm's law. And of course, the gradient of that graph, or the slope of that graph, is called the resistance, or is going to be the resistance. And normally, a graph of I against V is plotted, and that's why we call the IV characteristic graph. But for this, it's going to be the same graph, because if I plot I against V, it is still going to be the same because it's a straight line through the origin for I against V. So normally, a graph of I against V is plotted. And for a metal wire, the IV characteristic graph is the same as this one. However, the gradient or the slope of this is going to be 1 over R. So if I plot I against V, then the gradient is going to be 1 over R instead of simply R. So for a metal wire, the IV characteristic graph is going to look the same as this one here. As long as it's a metallic conductor, a graph of V against I is a straight line through the origin, or a graph of I against V is a straight line through the origin. But if it is V against I, remember resistance is equal to V over I. So if it is V against I, then the gradient is the resistance. However, if it is I against V, we have got the reciprocal, so the gradient of the slope is going to be 1 over R. You should note that very carefully. So we have now mentioned the IV characteristic of a metal conductor, or a conductor which obeys Ohm's law, but we haven't yet mentioned Ohm's law. However, we said it must be a straight line through the origin to indicate that I is directly proportional to V if the temperature does not change, if the temperature remains constant, and that is going to be Ohm's law. You should be able to sketch a graph of I against V or V against I for an ohmic conductor, or for a metal wire, or for a conductor which obeys Ohm's law. And I am saying it is simply going to be a straight line through the origin. So you should mark that very carefully. So let's talk about Ohm's law in more details. So we have seen in the previous part that the current must be directly proportional to the potential difference, or the PD, across the component, as long as the temperature remains constant. And I said that relationship is actually Ohm's law. So Ohm's law can be stated that the current passing through a metallic conductor at a constant temperature is proportional to the potential difference between its ends. In other words, current is directly proportional to PD at constant temperature. It doesn't make any good sense to say PD is directly proportional to current because the PD is the independent variable, yet the current is the dependent variable. So the correct way to state this would be current is directly proportional to the potential difference at constant temperature. Now, do not forget to include the part of constant temperature because the part of constant temperature is what makes this one valid, because if the temperature does not remain constant, as we are going to see later on with a filament lamp, the current will not be directly proportional to the PD. So such a substance which obeys Ohm's law is called an ohmic conductor, such as a metal wire or a copper wire and so on and so forth. And a graph like this one here that we have seen in the previous case where we got a straight line through the origin. Which kind of graph am I sketching? A graph like this one which we got for I against V, which is a straight line through the origin. So a graph like this one would be obtained for wires of any metallic conductor, provided that the temperature did not change. So the temperature should remain constant throughout the experiment. The length, of course, the length and the cross-sectional area of the wire have already been considered to be constant because it's the same wire. So we assume that the cross-sectional area has not been changed. The length has not been changed because all these ones affect the resistance of the metal wire. So it's like we have mentioned temperature, length, and the cross-sectional area are somehow affecting the resistance of a wire. So if you want the current to be directly proportional to the PD, the temperature should be the constant, of course, the length and the cross-sectional area of the wire not changing. So Ohm's law applies to metal wires provided that current is not too large, because we are going to see later on that some devices like the lamp, the filament lamp, only glows when the current is too large, that the lamp becomes very hot, or the filament of the lamp becomes very hot. And if it becomes very hot, means the temperature increases. So that means we shall later on see that for a filament lamp, the current cannot be directly proportional to the PD because the temperature does not remain constant. However, if the current is relatively smaller, then the current is going to be directly proportional to the PD because it will not cause heating. So the current must not be so great that there is no pronounced heating effect, causing an increase in the temperature of the wire. So for Ohm's law to be obeyed, the current should not be very large to cause a very big or a pronounced heating effect, which will cause the temperature of the wire to change. A pronounced heating effect will heat up the wire or cause the temperature of the wire to change. And if the temperature is not constant, the current is not going to be directly proportional to the PD. So that is for a filament wire. It is a straight line through the origin. Let's talk about the filament lamp. We have seen the metal wire. Let's talk about the filament. So the IV characteristic for the filament lamp is going to be surprising. Ohm's law does not apply to semiconductors such as diodes and filament lamps. Semiconductor diodes and filament lamps do not obey Ohm's law. Therefore, we don't expect their IV characteristic graphs to be straight lines. These ones are going to be called non-ohmic conductors. They are conductors which do not obey Ohm's law. In other words, for them, I is not directly proportional to the PD because the temperature may not be remaining constant, especially for the filament lamp. I is not directly proportional to the PD for a semiconductor because the semiconductor, we shall see, it starts conducting at a certain PD, not at any PD. So if we use a similar setup or a similar circuit that we used in the first case of a metal wire, where we have a rheostat, we have a device. This time we are replacing a resistor with a lamp. So we have our lamp here. Across the lamp, I put a voltmeter to give me the PD. Then I have an ammeter inside the circuit to give me the current. You must be able to draw this circuit diagram in an exam to verify Ohm's law. All we are replacing is we remove the metallic wire or the resistor, and we have put a bulb or a lamp. So if we try to investigate the lamp and obtain different values of V in volts and corresponding values of I in amperes, and we try to plot a graph. If you try to do this in the laboratory, the graph you will plot will take that shape. Experiments have shown that when V against I are investigated and plotted in a graph, the IV characteristic graph looks somehow like this. Of course, there is a small problem with this graph because it appears as if it is perfectly horizontal. I always discourage my students from sketching this graph to be perfectly horizontal because it changes the meaning of this. Remember, the gradient is of an IV graph is the gradient is equal to 1 over R. Now here, when the line is perfectly horizontal, it means the gradient is 0. And remember, R is equal to 1 over the gradient. If it is 0 gradient, it means 1 over 0 is going to be infinity. It means we have reached infinite resistance. Yet we can't reach infinity. Therefore, the best way to sketch this graph would be to just make this line to tend to be horizontal, but not perfectly horizontal, because making it to be perfectly horizontal would mean we have reached infinity. So just make it to tend to being horizontal to show that the gradient is decreasing, but we can't reach infinity. Okay, but essentially it is not a straight line, but is a curve of a decreasing gradient. It's a curve of a decreasing gradient. If you try to investigate this in the laboratory, obtain different values of PD across the lamp and different values of current, then try to plot a graph. The graph you obtain is going to be a curve of decreasing gradient. It is not going to be a straight line. Now the question is, what is really happening? So at first, it appears as if the resistance is constant, where we notice that is almost a straight line for the first part of the graph. At this point, the temperature is still constant because the current is even small. So it appears as if it is a straight line. But for the filament lamp to light, it must be red hot, orange hot, and so on and so forth. So what is really happening is that the resistance is going to increase where the line becomes a curve. In other words, the gradient is actually decreasing. Why is the gradient decreasing, or why is the resistance increasing? Of course, remember the resistance is equal to 1 over the gradient, and if the gradient is decreasing, it means the resistance is increasing. So at first, the resistance is almost seen to be constant, where we have a straight line. But then the resistance increases. That is where the line curves or the gradient decreases. This is because for the filament lamp to light, the temperature of the filament must increase to about 1500 degrees Celsius. The filament will only lamp if the temperature is high enough to about 1500 degrees Celsius. So a lamp filament consists of a thin metal wire, but it does not obey Ohm's law. So the IV characteristic graph is not a straight line through the origin. This is because the temperature of the filament does not remain constant. The temperature of the filament does not remain constant. For the filament to light, the temperature must increase to about 1500 degrees Celsius. And we shall see the relationship between the temperature and the color. That will be in a unit called astrophysics and cosmology. The relationship between temperature and color. If it glows yellow, what temperature should that be? When you put a metallic object on a burning flame, you see the colors of the object changing, so that it starts glowing to the colors which are visible to our eyes, which means For a filament lamp to glow, for us to be seeing the light coming from the filament lamp, it must do such at a certain temperature, which temperature corresponds to the wavelength that we see with our eyes. So, the temperature of the filament is increased, it doesn't remain constant. That's why Ohm's law is not obeyed. The temperature is increased, it doesn't remain constant. That's why Ohm's law is obeyed. So a lamp filament consists of a thin metal wire but does not obey Ohm's law. Uh, its IV graph, so its IV graph or its IV characteristic graph is not a straight line throughout. And I've mentioned that this is because the temperature of the filament does not remain constant. The increase in current causes the temperature to increase so much that the filament glows. So as more current flows through the filament so that the filament glows to give us light, the temperature of the filament increases to about 1500 degrees Celsius for the bulb to glow. And remember, the gradient of an IV characteristic graph is 1 over R, which means the resistance is equal to the gradient. When the line becomes horizontal, it means the gradient tends to 0, which means R tends to infinity. That is very important. As the line becomes horizontal, it means the gradient is becoming 0, which means R is tending to infinity. But I cautioned you not to make this line to be perfectly horizontal. However, just make it to have a decreasing gradient rather than making it to be perfectly horizontal. And I explained why it should not be perfectly horizontal. Making it perfectly horizontal would mean you have already reached infinity, and we cannot reach infinity. However, we can predict that the resistance is increasing to infinity, so it is tending to infinity. So you may not always sketch this as being perfectly horizontal, though in the exams many times it will still be accepted. So since we cannot reach infinity, then it would be wrong to make the line completely horizontal. When the line is horizontal, the gradient is 0. Because the resistance is equal to 1 over gradient, when you divide 1 by 0, of course you'll be getting infinity. So we can desist from making our graph to be perfectly horizontal because we don't want to assume that we have reached infinite resistance. In practice, we cannot reach infinity. However, we know that it is tending to infinity because it increases as temperature increases. So one factor which affects resistance is the temperature. In fact, resistance increases with temperature. Okay, we shall come back to that. Let's talk about the IV characteristic graph of a semiconductor or a semiconductor diode. What do we know about a diode, first of all? So I think a diode, we know from our IGCSE what a diode is. A diode is a device which conducts current in one particular direction. So a diode starts conducting not only at all PDs, but starts conducting current at a certain PD because it is a semiconductor where the electrons may not have enough energy to conduct, so they need to first gain some energy as the PD is applied across the conductor before they start conducting. So initially they will not conduct because they will not be having enough energy to conduct electricity. So a semiconductor will not be also an ohmic conductor. It will not be like a metal wire, even though it may be made out of a metal wire. So when a diode is tested in the same way as a filament lamp and a metal wire using the same circuit as we have seen, of course we shall have a graph which looks like this. We shall have a graph which looks like this. So using the same circuit where there is a filament lamp, I just replace this with the filament lamp with a diode. I think this is the positive end of the diode and this is the negative end. So If I record the values of V for a diode and several values of I for a diode and plot a graph, we notice that for a diode, it starts conducting at around 0.5 volts. And a diode is going to be said to be forward biased. If the current was flowing in the opposite direction, the diode does not conduct. That's why on the negative part, we have a horizontal line. On the negative part, we have a horizontal line. It wasn't the case with the filament lamp or the metal wire. So for a diode, on the negative part, because for it conducts current in one particular direction, it means if current is flowing in the opposite direction, it doesn't conduct. So a diode conducts current in one particular direction. That's why the negative part is along the x-axis. Then it starts conducting after a few volts, that is around 0.5 volts, then the diode conducts. You might also remember the symbol for a diode, which looks like that. Or of course, in an exam, there's a horizontal line, there's a line through this, and that is a diode. But a diode looks like this in the laboratory. If you check your laboratory, you'll see something like that. So this is the positive end of the diode, and the other one is the negative end. For the diode to conduct, the positive end of the diode must be connected to the positive end, the positive terminal of the battery. So the positive end of the diode must be connected to the positive terminal of the battery for the diode to conduct. If the current changes direction, it means now this becomes positive and this negative. Current is supposed to be flowing like this. The diode will not conduct. In that case, we say it is forward biased. It must conduct, or it will only conduct if the positive end of the diode is connected to the positive terminal of the battery. That is how the diode must be connected. So initially, the diode will not conduct in the negative if the PD is negative, and it will even not conduct not until a certain few volts across the diode are observed. That is when it will conduct. So the diode starts now conducting rapidly. What does that mean? Initially, for negative values of PD, resistance is infinity because there is no current flowing, up to a few volts. Then after a few volts, now resistance decreases because we see that now the diode starts conducting rapidly. That is the diode. So let's understand what the diode is in more details. Remember, you must be able to draw the circuit diagram. So diodes are made from semiconductor materials such as silicon. We also have germanium. The diode conducts when current is in the direction of the arrowhead on the symbol. So the diode will only conduct when current is in this direction shown by this arrowhead. Because this end is positive, the other end is negative. So it means the positive end must be connected to the positive terminal of the battery because current flows from positive to negative. So diode conducts only when current is in the direction of the arrowhead in that symbol. So we say this conduction is forward biased. The potential on the left-hand side of the diode is more positive than that on the right-hand side of the diode. If we try to reverse the PD or the voltage, we say we shall have a negative bias. Or this is called the reverse bias. The diode does not conduct when in the reverse bias condition. In the laboratory, you can try to connect a diode in the circuit and then reverse it and see if you will still have a reading. So as a result, diodes are used to convert alternating current into direct current in a device called rectifiers. We shall see rectification in a unit called alternating current, where we shall use diodes to convert alternating current to direct current. Because diodes force current to only flow in one direction or allow only current flowing in one direction, then we can convert current which flows in two different directions or in opposite directions to only flow in one direction. So that is what we call rectification. We shall talk about rectification in paper 4, A level. Or if you're already doing both AS and A level, just refer to AS. Just refer to alternating current in paper 4 in my videos because I've already recorded it. So the resistance of the diode is very high for low voltages in the forward biased condition. The diode conducts with a bias voltage of about 0.5 volts. For voltages above this value, the resistance of the diode now decreases. That's why we saw that for the graph. Initially, it was a line along the x-axis, and then at around 0.5 volts, the diode now conducts rapidly. So the diode conducts with a bias voltage of about 0.5 volts. For voltages above this value, the resistance decreases. So then we have a straight line after this point here. But does that mean Ohm's law is obeyed? Not at all. The straight line part of the graph in this region does not follow Ohm's law because it doesn't go through the origin, and therefore the resistance is not constant. Hence, we can't say that for a diode, current is directly proportional to the PD, not at all. Because even though after that we may have a straight line for a diode, but remember, this straight line does not go through the origin. Therefore, Ohm's law is not obeyed. For Ohm's law to be obeyed, the straight line must go through the origin. So that is a diode. If we reverse the current, if the current is reversed, or the PD is reversed, or the PD is negative, then the diode is going to have an infinitely high resistance. It will not conduct completely. Like I said, in the laboratory, you can try to connect a circuit which incorporates a diode. And if there is a current, reverse the diode and see if there will still be a current. So you will not receive a current, or you will not detect any current if you reverse the diode in the opposite direction, because in the reverse bias, the diode has an infinite resistance. It will not conduct at all. If you have a very low voltage, still the diode will not conduct. If you have a negative voltage, the diode does not conduct. It starts conducting at about positive 0.5 volts, because at this value, the resistance of the diode decreases. The reason as to why the resistance of the diode decreases at this value is now not part of what I'm supposed to explain. But if you are doing a curriculum where you studied the band theory where you explore the convalesce band, the forbidden band, and the conduction band, you now understand how semiconductors behave when a PD is applied across them. But for now, we just need to know the IV characteristic graph of a diode, that for negative values of V, the diode will not conduct, and for extremely low values of V, still the resistance is infinitely high, but the resistance decreases at around 0.5 volts, where the diode starts conducting and rapidly conducts. However, we can't say that Ohm's law is obeyed even if we have a straight line afterwards, because even if we have a straight line afterwards, the straight line does not go through the origin, so still we can say Ohm's law is not obeyed for a diode. So you should be able to sketch a graph for the IV characteristic, or the IV characteristic graph for a diode, where we said for negative values there is no conduction, the resistance is infinitely high. For the reverse biased side, the resistance is infinitely high. And even for lower voltages, the resistance is still high, not until we reach about 0.5 volts. That's when the diode starts conducting, and then we shall have a straight line. But I said this straight line does not go through the origin, and therefore Ohm's law is not obeyed. So that is for diode. In summary, let's summarize the three IV characteristic graphs that you expect to find in your exam. If we have a resistor or a metal wire, for a resistor or a metal wire, it is a straight line through the origin. Resistor, metal wire, metal conductor, we expect a straight line. If it is a filament lamp, we have seen that for a filament lamp, it is a line, a curve of decreasing gradient. I think this is the best way to sketch it and to avoid sketching it as a horizontal line. So for a filament lamp, it is a curve of a decreasing gradient. So this decreasing gradient means resistance tends to infinity. This one means resistance is constant. Then we have seen that for a diode, the IV characteristic graph looks like that, where it is resistance is infinity for the negative values, and resistance starts decreasing after around 0.5 volts. You should be able to sketch these three curves. So using the above circuit, try to obtain the I and V values for each component in the laboratory and plot the graphs to see if you obtain similar graphs. So of course you must be able to draw the sketch or the circuit diagram which we have been using. It has a power supply, it has a variable resistor, it has an ammeter. Then now you can put here your component, the component you are trying to investigate, and then you must put a voltmeter across. The component you are trying to investigate should be put there. You can check the resistor, you can put here a resistor, fixed resistor. This one is a variable resistor or a rheostat. This one you can use a rheostat. So here you can put a resistor, fixed resistor of say 5 ohms. You can put here bulb, your bulbs in the laboratory. You can put here diode, there are diodes in the laboratory. And then you try to record different values of V and different values of I and try to plot a graph and see if you don't get a graphs of this nature. But essentially your graphs will look like this. Okay, so those are the IV characteristic graphs for a metal wire or metallic conductor or resistor, a filament wire, and a diode. You should be able to sketch these IV characteristic graphs. Okay, so let's go back to the relationship between resistance and resistivity and other factors which affect our resistance. So we have been talking about temperature affecting the resistance because when we say that if the temperature is constant, I was directly proportional to V, which meant that the resistance was constant. But this was only true if the length of the conductor and the cross-sectional area remained constant. So it means it's like there are three major factors on which resistance depends. And these factors include, the factors on which resistance include, we have mentioned the temperature. So you may ask yourself, how does temperature affect resistance? We shall see that. We have mentioned length. You may ask yourself, how does length of a conductor affect resistance? We have mentioned cross-sectional area of the conductor. How does cross-sectional area affect the resistance? And one more other factor which we shall discuss later on is going to be the nature of the material. Some materials are naturally good conductors, others are naturally poor conductors. For example, we have a semiconductor material is naturally poor conductor. That is nature of the material. And the nature of the material is what we shall relate to resistivity of the material or conductivity of the material. Let's first understand the effect of temperature on resistance. Of course, we saw for the filament lamp at high temperature, the resistance also increased. So it's like resistance is directly proportional to temperature. If we have a longer conductor, we shall also see that the length of the conductor increases the resistance. If we have a bigger cross-sectional area, the resistance is going to be smaller. So it's like resistance is inversely proportional to cross-sectional area. And we shall combine maybe these two factors together with the nature of the material to come up with a relationship between resistance and resistivity. But let's first understand the effect of temperature on resistance. So how does temperature affect resistance? We know from our GCSE thermophysics that all solids are made up of atoms and constantly vibrating about their equilibrium positions. All solids are made up of atoms which are in continuous vibration about their equilibrium positions. From GCSE thermophysics, we also saw that the higher the temperature, the greater the amplitude of vibration. If we increase the temperature, the amplitude of vibration of the atoms which make up the solids would increase. We also mentioned in the first lesson that electric current is the rate of flow of charge carriers. So electric current is the flow of free electrons through a material. But as these electrons are moving through a material, they are going to be colliding with the vibrating atoms. So we already have vibrating atoms in the solid, and we have the free moving electrons in the solid. So it means the free moving electrons are most likely going to collide with the vibrating atoms. What does that mean? The movement of the free electrons, which constitute the current, is interrupted by the vibration of these atoms. So it means the more the atoms vibrate, the greater the chance of collision with the electrons. This means that the current is going to be less and the resistance is going to be greater. Hence, the resistance of metals increases with the temperature. So if we increase the temperature, or if the temperature increases, it means the atoms vibrate more and more violently. The vibration of the atoms affects the free movement of the electrons. And if the movement of the electrons is interrupted, it means the flow of current is being interrupted. That's why we are saying the higher the temperature, the higher the resistance. So resistance increases with the temperature. By the way, all materials have some resistance to flow of charge. All materials have some small resistance, it could be very small, to the flow of charge. As the charges move through the material, they collide with the atoms of the material which get in their way and transfer some of their kinetic energy to the atoms. And it is this transfer of energy on collisions that cause electrical heating. So you might have touched a wire which has been carrying a current, or you might have touched your charger after you have finished charging your phone, and you notice that the charger is hot or it is warm. The reason is very simple. The free moving electrons have been colliding with the vibrating atoms which make up the wire. As the free moving electrons collide with the vibrating atoms, they transfer their kinetic energy to the atoms, causing the atoms to vibrate even more. And the vibration of the atoms is what causes electrical heating, or what causes the wire to heat up. So to understand this, let's just look at or focus at a simple animation as shown here. So in a metal conductor or a metal wire, we have free electrons and we have atoms. The atoms of a solid are arranged in a regular pattern to form what we call a lattice. So the free moving electrons, if the temperature increases, the vibration of the atoms increases. So the free moving electrons are going to be interrupted by the vibration of the atoms. And as the atoms vibrate, they collide with the moving electrons, taking up some of their energy and therefore interrupting their motion. So these interruptions are the ones which prevent or reduce the flow of current in the circuit. That's why we say resistance increases, because as long as the free movement of the electrons is interrupted, then the flow of current is being interrupted. So we say the resistance increases as temperature increases. However, for a metal conductor, the higher the temperature, the faster the metal atoms vibrate, and the more likely they are to impede electron flow, hence increasing resistance. So if the temperature is high, the vibration of the atoms is also high. Therefore, they are more likely to prevent or to interrupt the free movement of the electrons. And I'm saying if the free movement of the electrons is interrupted, we say the resistance increases. Hence, we are saying resistance is directly proportional to temperature. Resistance is directly proportional to temperature. So if I was to sketch a graph of resistance against temperature, it is going to be a straight line. Unfortunately, I can't draw this straight line to the origin, because even at zero temperature, any conductor has some resistance. All metals, all materials have some resistance. So the resistance is directly proportional to temperature, but I'm saying the graph cannot go through the origin, because even at zero temperature, a material has some resistance. That's why the lines start from a certain point. However, pure metals have relatively lower resistance than impure metals as temperatures increase. Of course, the impurities also contribute to more resistance for non-pure metals. The impurities increase the resistance. That's why even at 0 degrees Celsius, the resistance of an impure metal is higher than that of a pure metal because the resistance also prevent the free movement of the electrons. The impurities also prevent the free movement of the electrons. That's why resistance of an impure metal is going to be higher than that of a pure metal. However, what is very important to note here is that resistance is directly proportional to temperature. And I'm saying this graph cannot go through the origin because all materials, even at room temperature or at 0 degrees Celsius, have some resistance, however small. Okay, that is the effect of temperature on resistance. Let's talk about resistance and the length of a material. How does the length of a material affect resistance? Let's consider three cylindrical objects of the same cross-sectional area but increasing length. So we notice that, or we shall notice that a longer material has a greater resistance. In other words, resistance is going to be directly proportional to length. And a shorter material will have a smaller resistance. So what I'm simply saying is that resistance is directly proportional to length. The resistance R is directly proportional to length. Then you will ask yourself, how is resistance increasing with length? So if we have a longer conductor, the charge carriers will have a longer distance to travel. And that longer distance to pass through or to travel through increases the chances of collision with the atoms. The electrons will have to move a longer distance, which increases chances of collisions with the atoms which make up this material. So, a material like this one has more atoms along it. So if a similar cross-sectional area has an equal separation of atoms, so it means an electron here has higher chances of colliding with these atoms compared to an electron in this one here, because there are fewer atoms which are vibrating in this case compared to the number of atoms in a longer material. So it means the longer the material, the high likelihood or the more chances of a charge carrier to collide with a vibrating atom. That's why I'm saying resistance increases with the length. Hence, the resistance of a wire increases when the length of the wire increases. So we are saying resistance increases with the length. How does cross-sectional area affect resistance? Let's look at cross-sectional area and resistance. So let's compare let's compare 1, 2, 3, 4. Let's compare A and B. These ones have the same length. I mean the same cross-sectional area, but different lengths. And these ones also have the same cross-sectional area, but different lengths. So if I compare this one and this one here, same length, different cross-sectional area. So imagine you are trying to move in a class which has 40 chairs, and those chairs are supposed to be arranged side by side. If the class is widened, it means it is easier for you to find space between the chairs for you to pass through or to go through the class. If the class is narrowed, it means it is harder for you to find space for you to go through the class. What does that mean? It simply means that the resistance of a wire decreases when its cross-sectional area is increased. The same way it is easier for you to go through a class which has 40 chairs when the class is widened. Widening is the same as increasing the cross-sectional area. So if the cross-sectional area is increased, it is easier for you to go through. Being easier to go through means the resistance is decreased. So we can look at these two materials and say, if the same number of atoms, for example, the same number of atoms are now in a bigger cross-sectional area. It means here an electron can easily pass through this material than it does through a narrow material. So resistance decreases with increase in cross-sectional area. So the thicker a wire is, the smaller its resistance. Bigger thickness means bigger cross-sectional area. So wire C is thicker than wire A. So the thicker the wire is, the smaller its resistance. This is because there is a bigger area for the charge to travel through, while with less chance of collision. So the bigger the area, the smaller the chance of collision of the electrons with the atoms, and therefore the smaller the resistance. Hence, we simply say resistance is inversely proportional. Resistance is inversely proportional to the cross-sectional area. So now let's combine these factors that we have talked about. In summary, we have said resistance is directly proportional to temperature, resistance is directly proportional to length, resistance is inversely proportional to cross-sectional area. But remember, also resistance depends on the nature of the material, which we shall call the resistivity, and the conductivity or conductivity. So resistance also depends on the nature of the material or the type of the material. For example, we know that copper is naturally a good conductor, whereas plastics are good insulators. That is nature. So the measure of the conductivity of the material, or the measure of how much a particular material opposes electron flow, is what we are going to call the resistivity. We have said resistance is directly proportional to temperature. The higher the temperature, the higher the resistance. Resistance is directly proportional to length. The higher the length, or the longer the length, or the bigger the length, the bigger the resistance. And the resistance is inversely proportional to cross-sectional area. Because this is a physical factor, environmental factor, we shall combine these two factors to come up with an expression which relates resistance to the nature of the material. So we shall simply see that resistance is directly proportional to L, but inversely proportional to the cross-sectional area. I will remove the proportionality sign. Resistance is going to be equal to L over A. I must introduce a constant, and this constant will be called rho. Therefore, we say resistance is equal to rho L over A, where L is the length of the material, A is the cross-sectional area, and rho is going to be called a constant, which depends on the nature of the material, and this constant is going to be called the resistivity, or the specific resistance, or you can call the conductivity, even though it is rarely called the conductivity of that material. Remember, cross-section area A could be given by pi r squared. And also remember that the radius is equal to diameter divided by 2. So many times cross-sectional area will be quoted as pi d squared divided by 4, because r is d over 2. When you square, you get d squared over 4. So I'm saying rho is the resistivity, or the specific resistance, which is a constant for a particular material. As long as it's the same material, it is a constant for that particular material at a constant temperature. If the temperature is not constant, of course, rho is also not going to be constant. For example, if it is a semiconductor has different resistivity at different temperatures. So at the constant temperature, the resistivity, or the specific resistance, is the same for the same material, even if it has different lengths or different cross-sectional areas. And making rho the subject, the resistivity of a material could be given as Ra over L. We can derive the units for resistivity. R is measured in ohms, area is measured in meters squared, length is measured in meters. So it's like the resistivity is measured in ohm meters as the unit for resistivity. So the unit for resistivity is going to be the ohm meters. The unit for resistivity is the ohm meter. I'll give a simple example here. A nichrome wire of diameter 3.1 times 10 to the power of minus 6 meters has a resistance of 100 ohms. The resistivity of nichrome is 1.1 times 10 to the power of minus 6 ohms. Find the length of the wire. So this is diameter, this is resistance, this is resistivity. Remember, we said resistance is equal to rho L over cross-sectional area. And we also know that cross-sectional area is equal to pi r squared, which is the same as pi d squared divided by 4. So it means we shall have resistance as being equal to rho L divided by pi d squared over 4, and the 4 will go up. So resistance is going to be 4 rho L over pi d squared. I want to find L. I can make L the subject, so L can be R times pi d squared divided by 4 times rho. So I can now substitute in that equation to find the length L. So in our solution, resistance is equal to rho L, and when I make L the subject, L is going to be equal to R pi d squared over 4 rho. When I make substitution, R is 100 times pi times 3.1 times 10 to the power of minus 6, but it is squared, divided by 4.11 times 10 to the power of minus 6. And this gives me L as 6.86 times 10 to the power of minus 4 meters. So you should be able to solve questions which involve using the expression R equals to rho L over A. You should be able to solve such questions. For more examples, do not forget to visit the solved past paper questions in one of the playlists called Electricity and D.C Circuits, both multiple choice questions and short structured questions. I think let lesson 3 stop here. See you in lesson 4. Until next time, bye bye.